Hi everyone, today we're going to talk about improving deep learning model robustness for better performance over time. I'm Yonatan, the CEO and co-founder of Deci. So we'll talk about what is model robustness, why it's important, how we take models from the lab to production, and how we prevent performance degradation in deep learning models in that switch from being in the lab to deployed in production, what affects the model robustness, and some best practices on how to improve the model robustness, one from the architecture design perspective and from the training techniques and data perspective. So first, model robustness is the ability of a neural network model to maintain its performance and generalization capabilities when faced with either adversarial inputs, perturbation, or change in the input data distribution. We train that model on a training data and then we deploy it, and the data that model sees in production is not the same. It's captured in a different way. It has some changes in the data, and we want the model to perform as similar to what we've seen in the training phase or in the lab when we tested that model just before we deployed it. So a robust model should make accurate prediction and avoid overfitting even when presented with noisy, incomplete, or out of distribution data. That's basically what we expect from the model by saying that it is robust. The traditional AI development workflow is suboptimal in the sense that people usually take some open source model, train it or fine tune it on the data set, then test it and then deploy. Usually those models either are good or sometimes we have overfitting or underfitting because of the model selection, and then we need to change that model, maybe try different hyperparameters when we train them and iteratively find the best way to build that model until we get it to the right point and we can deploy it. So basically, open source architecture are almost always not an optimal starting point for the model, and we have to choose several models and try and iterate on the model itself. The base assumption is that the capacity of the model is not optimal for the data, and we see underfitting and overfitting, and those have impact on model robustness and the training techniques, hyperparameters, and other aspects that considered during training can impact the training results, and by that also the model robustness. Over-parameterized models tend to either having bad confidence calibration, so basically the soft output of the models are not as accurate or not consistent, and unexpected behavior in out-of-distribution scenarios when we have some data perturbation or changes in the data compared to the data that the model have seen in the training. Let's understand a little bit about the mathematical aspect of model robustness. And when we look on the theory, mathematically model robustness can be defined using the concept of Lipschitz continuity. A function is Lipschitz continuous if there exists a constant Lipschitz constant that we denote as L, that for all the input x and y, the following inequality holds, which basically means that if we change the input, the change in the output is bounded by some constant with respect to the change in the input. F in this case is the model, and as the model become more and more complex, there is weaker guarantees about what is L or what is the bound on the changes on the prediction. So if we can think about it, we can make a small change between x and y, and when L is large, we can get a completely different output from the model, and this is not a good behavior that we can take to production. So the idea is that we need models that are robust, that L is as small as possible. And in the extreme case of a linear regression model, where we denote as y equal ax plus b, the constant, the Lipschitz constant will be the a, the slope of the linear function, which basically means that we have a nice Lipschitz continuity on that aspect. So that's an example of simple model that have nice properties of robustness with respect to perturbation in the X, but as models are getting more and more complex, we don't have that nice guarantee. Also, when A and X are vectors, this makes things even more complex because of the curse of dimensionality. If we want to improve the model robustness, what we can do is better design the neural architecture or use some regularization techniques for the model to improve the convergence and the robustness of the model, the resulting model after the training phase. So first we'll talk about better architecture design. So we talked about that most neural network architectures are usually found in academic research and trained on large data sets, and then sometimes we take them, fine-tune or train from scratch, and those are not optimized or adapted to the data that we're using at the moment. Our data set could be small, could be large, could be with small variations, could be with large variation between samples, and there is usually no adaptation between the architectures that is fixed to the model itself. This is an example of how the model size, the data size impacts the total accuracy, the validation accuracy of a model. What we can see here is an example on the Cypher-10 dataset from a paper that incorporates neural architecture search with active learning. And what we can see on the x-axis that at each point in this curve, we can see two different architectures. One of them is very small, which is the blue. One of them is very small, which is the blue. One of them is very large, which is the red. And the black is when optimizing the neural architecture for each and every point in the process. And what we can see that we get better accuracy when the architecture is optimized for the dataset size. So this is one of the examples of how important it is to optimize the capacity or the size of the neural architecture to the size of the dataset. And underneath that paper, there is the use of neural architecture search, which optimize the structure of the neural network with respect to the data, which is also something that we're doing at Deci, where the data characteristics, either a small, large data set, for example, in object detection, we can think of multiple types of objects, small object, large object, that all impact the design of the model in order to get the maximum accuracy, but also the best generalization capabilities. And this is the idea of designing neural architectures that can fit exactly the data characteristics that we want to train on or we want to build a model on top of. The extreme case of model robustness or lack of model robustness is what is called adversarial examples. What we can see here is that in the case of adversarial examples, we make a small perturbation in the input to the model, and when checking the model without the perturbation, we get one prediction with some level of confidence. And when we add that noise, epsilon multiply by an image that is actually a noise that is found in order to attack that neural network, we get a completely different class with very high confidence. And here we see an example because of both changing completely the class and also perturbating the confidence level of the network in its prediction. While this is an extreme case that is tailored specifically in order to attack this network, some less impactful attacks or perturbation can yield small changes in the prediction of the model that can also make false prediction or impact the confidence level of the model with its prediction, which sometimes help us monitor the predictions of the model and make sure that these models are making kind of good predictions in the production environment. So if we can think about it, what can happen is that we're training a model, we're testing it in the lab, then we deploy it in production, and because of the data in production is different than the data in the development phase, we can get a completely different confidence level or even wrong classes because of that perturbation. And what we want to make sure is that the model will be robust and we'll be able to see the model will be able to handle those changes in the input and still predict the right class, and also have the confidence level that is derived from the model with the same guarantees or the same behavior as we saw in the training phase. The second aspect is how we train that model. So good training can improve the model robustness by converging to better minima, and by that we can improve the ability to overcome some perturbation or noise in the production environment that we are seeing. We will cover a few best practices and techniques in order to overcome or in order to improve the robustness of the model with training techniques that we can apply during training. All those methods are built in SuperGradients, which is an open source to train deep learning models, and you can use them either in SuperGradients or any other deep learning framework and build them based on those papers and examples. So exponential moving average is a technique to average the weight with an EMA, and that's increased the stability of the model conversion and help to get to an overall better solution or better minima and prevent the convergence to a local minima. What we can see on the right is the same model. One time it's trained without EMA, which is the green, and on the blue line it's trained with an EMA, and what we can see that the line of the blue curve of the convergence of that model is converged much better or in much more smooth way compared to the green one, and also resulting with a better validation loss in this case. Obviously, also things like increasing the batch size is something that can stabilize the training and reduce the risk of entering into some local minima and converging to that local minima. In the EMA, between steps of the convergence, we can also average at the end, the weights of the model in order to even get improved results. Another technique is weights averaging. Weights averaging is a post-training method that takes the best model, weights across the training, like multiple checkpoints across the training, and average them in order to get final weights, which is the average of, in this example, the three weights, W1, W2, and W3. And in this curve, what we can see that it helps us get into a better minima that is found through averaging of those checkpoints. If we want to think about the model robustness, or basically how changing the input affect to change the loss in this case, what we can see is that the final weights are located in this example, which is a schematic example, located in a flat minima compared to each of those three weights checkpoints that are located kind of on the slope. And that flat minima is something that improved the robustness, since what we can see that if we change the weight a little bit, the loss value will be the same, and we can think about translating the modification in the weight to the modification in the input as the property of robustness, as we talked earlier. Also, data augmentation is something that helps to prevent that changes in production over time. Usually the images are captured in different poses, in different sensors that sometimes have different statistics and color aspects and lighting. So in the modern data augmentation techniques, we can do some random crops, resizing to change those aspects of pose and size of the image, doing some changes in interpolation to overcome some artifacts that are based on encoding, decoding of images, and resizing of images. Also, color jittering is something that is helping to overcome some lighting condition that can change in the production environment, and also cut, mix, and mix up are good techniques for data augmentation that can mix several images in order to extend the data set into some images that are not in the training data set, but kind of enhance and enlarge the training set that we are training on, and by that improve the generalization of the resulting model, since it saw some kind of interpolation between images in the training data set. SuperGradients is an open source library for PyTorch models that help improve performance, simplify the training, and shorten the training time. All the features that I showed earlier are in that library, and people can use them in order to improve the model robustness, get better accuracy, improve performance, and simplify the development of deep learning models. And that's it. Thank you very much.